Welcome back, math enthusiasts. Today we are going to talk about the application. What that means is word problems. The application of rational functions. So we're going to talk about real life word problems of real things that happen in real life that use fractions. Right? And I know this is where your most terrifying moments of your entire life have been lived, right? They've been just in the muck, wandering around outside at night in the dark, and then a wild fraction runs up on you and asks you to reduce it. And ever since then, you've had this fear of fractions, right? It's a phobia. Mr. Barton, I had an experience once. A fraction nearly killed my entire family. I know, kids. But listen, you were like 3 years old. It was someone's fraction that had gotten out. It ran up. It licked you on the toes 3 times. And then you went, oh, it licked me, Mom. And then your mom picked you up. And then your dad went, oh, what a cute fraction. Better figure out where he lives. That way he can get home to his family. But that doesn't stop you from being terrified of fractions because you were 3 when you first had this encounter. And now, ever since, you've been scared. So what we're going to do is we're going to face our fears. We're going to do some word problems with fractions today. We'll make it okay. Maybe at the end you'll go, oh, maybe I do like fractions. I'm going to get a fraction. I'll let it live in my house. It'll lay on the foot of my bed every night, keep my toes warm, and then in the morning we'll go on a walk. Hopefully. But probably not. Probably not. You guys probably will still hate fractions, but c'est la vie. I tried my best. All right, before we get into talking about rational functions, let's talk about 2 things that you probably already know in a math context, but you might not have a nice visceral, guttural, spiritual understanding of these things. The first thing we need to talk about is a rate of change. And you're going to say, Mr. Barton, that's just the slope. I know it's the slope. Like I said, you understand it in a math term. We want to understand it in real life. A rate of change is a ratio describing how 2 variables are related. So let me give you a couple of examples. Let's say you go to the gas station and you're going to buy a bag of Fuego, what are they called? Takis, right? Fuego Takis. Fuego Takis. Because those things smack, right? So you get your one little bag of Fuego Takis. Here's your bag, right? There. Fuego. Here, no. Let's just put the symbol for Fuego, you know. There we go. Fuego Takis. That's terrible. Let's try that one more time. I can draw fire better than that. What's Fuego look like? S's. That's the trick. You gotta just make big S's. There we go. Fuego Takis. And these things smack. I love these things. But you go to the gas station and you buy this thing. And it's the gas station, right? So they gotta charge you way too much for this bad chicken. And you get a regular size bag. Let's say it's $2 dues. Okay, they charge you 2 schmeckles for this thing. This bag of Fuego Takis was $2. So you're gonna say, Mr. Barton, this isn't a ratio. What are you going on about, you nutcase, right? Consider this for a moment, children. This was $2 per 1 bag. This is the relationship we're talking about today. We're going to use these fractions where it's a certain amount of something, one variable, in this case the variable is dollars, over another variable. In this case, it's bags of Fuego Takis. So we can relate the price and the unit, I guess, the bag. It's 1 unit of Takis. It's 1 bag of Takis, right? So when we're talking about rates of change, what we're going to try and do today is we're going to try and set up these fractions that relate the two variables we're talking about. In most of the examples, it's going to be time and something else. But don't let my poor examples limit your imagination. You could do dollars per bag. If you're into cross country or something like that, you could do miles per minute or minutes per mile. A lot of runners, they go, I run 5 minutes per mile for cross country, and I do that for however far they want to hurt themselves for, you know. You could also put this in grams per ounce, right? 28 grams per single ounce. You could do points per game. Don't let my examples limit your imagination. All right. Next, let's just take a peek at this slope-intercept formula and maybe change this from mathy variables to something that means something to us in real life. So we're going to pretty much ignore the plus B for today. We're not going to start with any bags of Takis. We're going to just have 0 bags. I don't like starting with any. I like to start from ground zero and struggle my way all the way to the finish. So no y-intercept today. Let's look at just this y equals mx. You know from vocabulary that m is the slope, but instead of m, let's think about that as a rate. So we have rate is going to be multiplied to something. And what that's going to give us is y, or output. You want to think of your y as your total today. So the total amount of things I have is the rate times something. And this something is always going to just be whatever the bottom unit of our rate is. So if this is $2 per bag, this would be times the number of bags, because the bottom variable should match this. And that'll tell us the total amount of money we spent on Takis. Total dollars. So maybe let me give you a super easy example. Let's say it's $2 per bag of Takis. $2 per bag. And we could put per one bag. 2 over 1 is still 2. Times how many bags do you and your homies want? Let's say 5. You want 5 bags. We got to go acquire 5 bags. All right. So $2 per bag times 5 bags. That's going to give us $10 that we have to spend on Takis. So the rate times whatever the bottom thing of the rate, maybe the number of things. Instead of something, we could put number of things. Things. How do you spell things? Like that. So it's our rate times the number of things will give us the total number of the other thing. All right. So this is not necessarily what you're taking notes on today, but this idea of instead of y equals mx plus b, a total equals a rate times something, then that'll help us get to the answer probably a little bit better. Let me give you some pro advice from a professional. That's me. You can tell that I'm a professional because you're watching my YouTube channel right now. So let me give you some hints. Normally I would charge people something like $300 an hour to get tips, but because you go to a public school, you get it for free 99. So some pro tips from a pro on word problems. The first thing you want to do when you are doing a word problem is go through the problem and collect your information. What that means is you're going to turn your words that you see in the problem into numbers. You need to extract the numerical information from the problem because we're trying to do math with it. I can't do math when it's covered in English. All right, we got to wipe all the English off of it, shake it out, rinse it off, distill the math. All right, we got to get just the numbers out of that bad boy, and then we can finally use our math on it. Once we have some numbers, we want to make sure our units match. And what this is going to do for us normally is it just means if I have $2 per bag and I want to buy some other chips. So let's get some what other kind of chips do you guys like? The only thing I ever see kids eat is Takis. Flamin' Hot Cheetos. Those are cheaper, right? Those are $1.50 per bag. We just want to make sure that this is dollars over bags and dollars over bags. We don't want to accidentally write this as one bag is $1.50, because then our dollars and stuff is all crisscrossed. We want to make sure everything matches all the way through the problem. Okay, so just make sure all our units line up. That'll help us organize everything. Then at the very end of your problem, look at your answer and ask yourself, does that even make sense? I can't tell you how many times. Yes, I can. Let me try and tell you. It seems like every class I make this big point. I draw all over the board. I say, ask yourself. Ask, right? Ask yourself a question. Does this seem reasonable? If I have $2 per bag of Takis and I buy 10 bags, does it make sense that I just spent $1 million? Does that make sense? Do you think 10 bags of tortilla chips with some red stuff on them should be $1 million? I don't. But kids will write this. They'll go, well, that's what the calculator said. I don't know. I didn't even think about it. Well, that does seem a little bit high for 10 bags of chips. So once you're done, ask yourself, does it make sense? So if you have one person doing a job and it takes them 4 hours, then they get help doing the job the next time. Do you think it should take them more time to do it or less time? That's what I'm talking about. You want to ask questions like that. Does it make sense that more people helped and it took more time to do the same job? No way. So ask yourself at the end and see, did you get a reasonable answer or is something fishy going on here? Are you guys prepared? Take a deep breath real quick. Center your chi and we're going to do an example. This first example is called Many Hands Make Light Work, because you need help when you do stuff, otherwise it takes too long. So this is just example number 1. It says, Zach can clean the entire house in 3 hours if he does it by himself. Emily can clean the entire house in 4 hours if she doesn't get help. And Emily's my wife, Zach is me. I read her this question. She was livid. She said I should change these. She said I should swap them. How dare I imply that I could clean the house faster than she could? But then I explained to her, look, you have me put stuff on the top of the shelf. If you had to do this by yourself without help, you'd have to go get a step stool. She also has much higher standards for cleaning than I do. So whereas I would just wipe the top of the stove and call it good, she's going to spray the front of that bad boy and then wipe it down clean. So she does more stuff, so it's a little cleaner, I guess. But it takes her more time. So once I explained that she's just a perfectionist, she was okay with this problem. So I got her consent to put her in this problem. Don't worry about it. So we want to know, how long would it take us to clean the house if we work together? Because that's really what marriage is all about. It's about suffering together. So let's go through and use some of these pro tips. Let's collect our information first. Let's see. It says Zach can clean the house in 3 hours. So on all these problems, we're going to try and write these as rates. And I think after this example, it'll be a little clearer, right? But I have to just show it to you. It's hard to explain. So what I'm going to say is I'm going to put Z for Zach. This is, I can clean one house per 3 hours of work. So in 1 hour, no, excuse me, not in 1 hour. I can clean one house in 3 hours. So that's my rate of cleaning. You could also think of this as a third of a house per hour. So if it takes me 3 hours total to clean the house, if I only work for 1 hour, I'll only be a third of the way done. So you can either think about it in integers of stuff or as a fraction of a house in a single hour, whichever way you like more. All right, let's go get Emily's information. She can clean the house in 4 hours. So let's put a little E for Emily. This is one house per 4 hours. Now we want to know, how long would it take them to clean the house if they work together? So we are looking for what I'm going to call our combine rate. Sort of. I'll show you and then we'll expound upon it. So our combine rate is a mystery. How long combined would it take us to clean one house? We don't know. We don't know how many hours. So we're going to put a variable here as a placeholder because that's what variables are. It's a number we don't know. We'll call it T for time, hours. Alrighty. So we need to figure out, what is this T? How long would it take? That means how many hours. So we're going to figure this out. Our combine rate, if we work together, C equals Z plus E. It's how fast I clean plus how fast Emily cleans is going to be how fast we clean together. So now let's start plugging in some of these rates and we'll see if we can get T. So our combine rate is 1 over T. And I'm going to omit all the units here just for actually, let's not be lazy. Let's be a good teacher for once in our life. 1 house per T hours is equal to 1 house per 3 hours plus 1 house per 4 hours. And again, we are trying to get this T by itself. So the first thing I need to do is I need to add these two fractions together. And I know, you're terrified, but let's think back to 3rd grade. How do we add fractions? Mr. Barton, we need a common denominator. Ugh, I know, that's why you guys are in honors. So we need to make the bottom number the same by multiplying the top and bottom of these to get them to match. So we need to think of the least common multiple, the LCM. I bet you haven't heard that since 3rd grade. We need to find the LCM of 3 and 4. So if I look at multiples of 3, I got 3, 6, 9, 12, spoiler alert. And then if I look at my multiples of 4, it's 4, 8, 12. The first number they have in common is 12. So we're going to multiply these to get them to be 12s. On the left side, don't mess with that. Just leave it. It's 1 over T equals, to get 3 to be a 12, I need to multiply by 4. So we're going to do times 4 on the top, times 4 on the bottom. So 4 times 1 is 4 over 12. Plus, to get 4 to be a 12, I need to multiply this by 3. So that's going to be 3 over 12. All right, so let's add these together. And I know my units went away, but it's house, hours, house, hours. Now that these match, when you add fractions, the bottom stays the same, so it's still 12, and then the top gets added together. So that's 7 over 12. And this equals 1 over T. So this is 7 houses that Emily and I could clean together, but it would take us 12 hours. We want it to be 1 house, and we want to know how many hours that would take. So now we just need to get the T by itself. We could multiply both sides by T and then do some fancy arithmetic, but when we have 1 over T, I want T over 1. I want just regular T. So what we're going to do is we're going to take both sides of this equation and just do the reciprocal. So if I flip this could be 12 over 7. The units stick on the numbers, so this is hours per 7 houses equals T hours per 1 house. Okay, so T over 1 is just T hours per house. And then it equals this. This is your answer. It's 12 over 7. So it's 12 over 7 hours per one house. So that's the answer, 12/7 hours. If you want this in a little bit nicer number, I converted it. 12/7, this is about 1 hour, right? 1 hour and 43 minutes. Right? If you turn this into a mixed number, it'd be 1 5/7. So 1 hour and almost 2. There you go. So if we work together, we can clean our whole house in 1 hour and 45 minutes. That's way faster than 3 or 4 hours. So let's ask ourselves, does this make sense? Does it make sense that 2 people could clean a house faster than 1 person? Absolutely. So that passes the does it make sense check. Okay. I get that that's a little convoluted. If you're stuck, go watch it again. Or if you're brave, go watch the next example. But if you're actually stuck, don't forget, when you get back on the WebEx, say, Mr. Barton, you taught too fast, you told too many jokes, I got lost. Can we go over it one more time real quick, pretty please? And I would love to. All right, let's talk about a slightly different version of that same problem. This is a little bit harder, but we'll be okay. So we'll call this one speedrunning puzzles. Alan and Itati are going to do a 1,000 piece puzzle, and it takes them 7 hours to get that thing done. It's a big honking puzzle, you know. 1,000 pieces is not child's play. This is a woman's puzzle, you know what I mean? Not some little girl's puzzle. This is a grown woman's puzzle. They've both done the puzzle by themselves before. It took Alan 1.5 times as long as it took Itati to do it when they did it alone. So that means however long Itati took, Alan took 1.5 times longer. So if Itati took 2 hours, Alan took 3. If Itati took 4 hours, Alan took 6, right? You take Itati's number and multiply by 1.5 to get Alan's. We want to know how long did it take them each to do the puzzle individually. We want to know what's Itati's time and what's Alan's time. So we're going to go through and get all of our information first, and then we'll look at some equations and figure out how to solve this problem. So Alan's time, Alan's rate is unknown. He does one puzzle in an unknown amount of time. So we're going to put a little t, and I'm going to put a subscript. Subscripts are not math operations. They're like notes to the person doing the problem. So time, well, I'm going to have a time for Itati too. So to make sure I know this is Alan's time, I put a little capital A next to it so that I can tell which time we're talking about. So this little A just means it's Alan's time. So Alan does one puzzle in however long it takes him, and let's put this in hours because this is in hours. All right. Likewise, Itati can do one puzzle in however much time it takes Itati to do a puzzle. All right, so that's Itati's rate. We don't know what it is. That's what we're looking for. How long does it take each of them to do the puzzle? But we do know their combined rate. Together, Alan and Itati, while chatting away, flirting, you know, whatever it is kids do these days while they do puzzles, they did one puzzle in 7 hours. So we know the combined rate. All right, let's kind of check this other problem and make some comparisons. Before, we knew the individual rates and we were looking for the combined rate. And then we said the combined rate is just the two individual rates added together. So what we have is kind of the backwards of what this problem is. We know the answer, the combined time, and we're looking for these two individual times. So what we're going to do is we're going to start by writing this equation, and we'll talk about why we get stuck. So my combined rate is equal to Alan's rate plus Itati's rate. So this is going to be 1 over 7. One puzzle per 7 hours is equal to one puzzle over the number of hours it takes Alan plus one puzzle over the number of hours it takes Itati. Now we want these two t numbers here, but we can't solve for them. The reason for that is because this is one equation and we have two unknowns. There's a rule in math, or probably a theorem or something. If I thought you would remember it, I'd tell you the name of it. But there's a rule that says however many variables you have, you need that many equations to solve the problem. So because we have two variables but one equation, we don't have enough equations to solve this. We can't figure it out the way it is. So we need to make one more equation to help us out. That's where we're going to use this statement. Alan takes 1.5 times as long as Itati. So let's go write that as an equation. Alan's time, let me be consistent with variables here. Alan's time, so T Alan, equals 1.5 times the amount of time it took Itati. So what we're going to do here is some substitution. We're going to take TA, which is right here, and we are going to substitute it with 1.5 Ti. So this here will turn into 1.5 Ti. So now we have Ti and Ti. That's only one variable. It's in two places, but it's only one single symbol, right? It's both Ti's. So because we only have one variable after the substitution, now we can solve this problem. So this equation lets us make a substitution that makes this equation solvable. So let's go do that. So now we have 1/7 equals 1 over 1.5 Ti plus 1 over Ti. Capital I. And I've gotten rid of all the variables so that we don't get lost in the sauce. Now, just like we did on the last problem, we need to get a common denominator so that we can add these. So they both have the Ti. This one is missing the 1.5 though. So we're going to do times 1.5 on the top and the bottom. So we have 1/7 equals 1 over 1.5 Ti plus 1.5, because 1.5 times 1 is 1.5, over 1.5 T, lowercase t, I. And now because the denominators match here, we just add the tops. So 1 plus 1.5 is 2.5 over 1.5 Ti. All right, so now this is super easy to solve. We have 1/7 equals 2.5 over 1.5 Ti. What you're going to do is you're going to cross multiply basically. You're going to multiply those two together and those two together and set them equal to each other. So 1 times 1.5 Ti is 1.5 Ti equals 7 times 2.5 is 17.5 number. There you go. So to get Itati's time, we just divide by 1.5. 1.5 on both sides. So Ti equals, let me check my notes, ladies and gentlemen. This is 11.66 repeating, or 11 2/3 hours. If you should read your homework questions and figure out how they want it. It's probably this round to the nearest 10th or something. So just make sure you read how they want you to round. If they want an exact answer, we'd have to put it as a fraction. So this is a improper fraction, would be 35 over 3. Either way. So it takes Itati 11 hours and 40 minutes to do the puzzle by herself. Does that make sense? Well, together they did it in 7 hours. So it makes sense that it should take her a little bit longer. Maybe Itati's really good at puzzles. And now you're going to say, but Mr. Barton, what about Alan's time? Now that we have Itati's time, we can take that number and plug it in to this equation that we made, this easy one. To get Alan's time, it's just 1.5 times Itati's time. So if we take her 11.66 repeating, and then we multiply that by 1.5, that'll give us Alan's time. And let me just go ahead and double check that. I think it's 17.5 hours. Okay. All right, so there are our two answers. Again, if that was a little confusing, go ask for help. All right, we have one more question, and this one's a doozy. You got to put your big boy pants on for this one. Make sure you wipe your nose. Have your mom help you tuck in your shirt before you start this one, and then we're gonna be done. All right. So home is where the Wi-Fi connects automatically. You own a concrete company. Congratulations. I know. It's just what you always wanted when you grow up. I want to be a concrete guy, Mom. And you're pouring foundations for some new homes. You won the contract and you get to pour all the slabs for all the homes in this neighborhood. Congratulations, you made it to the big time in the concrete industry. You have 2 concrete trucks, and if you use both at once, it takes 40 minutes to pour the foundation for one home. And I have no idea how long that actually takes. So if you are actually a concrete person and you're like, that's so slow. All right, you got little trucks, dude, my bad. I don't know how long that actually takes. What we do know, though, is that the large truck can pour a foundation 25 minutes faster than the small truck. How long does it take for each truck to pour the foundation? So this question is very, very similar to the one we just did. We are looking for the, where does it say? How long? So we're looking for the time for each truck. We're looking for time large truck and time small truck. How long does it take one truck to pour one slab of concrete for a house? So that's what we're shooting for. Let's start by picking out all of our information and writing it down as some rates. So what we know right away is our combined rate. If you use both at once, it takes 40 minutes to pour the foundation for one home. So that's 40 minutes per one house. All right. Now we want to know what are the other 2 rates for our big and small trucks. So I'm gonna put B for big truck, or let's be consistent. I'm being inconsistent, which is bad because it's confusing. Let's use L, large truck. So the large truck takes, we don't know. So we're gonna put a variable, TL minutes. And I'm using minutes here because the question is in minutes. You want to make sure your units match. So it takes TL minutes for the large truck to pour one house worth of concrete. For the small one, it's going to take TS minutes to do one house. This is going to work out. I don't think it is. I think I messed up a little bit. I think we actually need the time to be on the bottom. Yeah, let's flip all these. Sorry. L equals 1 over TL. S equals 1 house over TS. And then our common rate is 1 house in 40 minutes. I'm just going to do it this way because that's the way I did it on my notes, and I don't want to mess myself up and tell you the wrong answer. I think it might work the top way. If you really want, you can try it on your own and see. If it doesn't, let me know and maybe we can talk about it. But we'll ignore this. We'll use the bottom ones. So this is one house in TL minutes, house in TS minutes, and our combined rate is one house in 40 minutes. Generally, I just like to have the bigger number on the bottom. I like my fractions to be fractions, not improper fractions. But again, that might be personal preference. I'd have to think about it. All right. So we know from all the other problems that our combined rate is equal to our sum of the other two rates. So the large rate and the small rate. Now we're just going to make some substitutions so it looks more like an equation. So our combined rate is one house in 40 minutes. L is one house in TL minutes, plus our small rate is one house in T small minutes. All right, just like this problem where we are doing puzzles, we have two variables in this equation. We have TL and TS. So we need to figure out one more equation to be able to change one of them into the other one so that we only have one variable. That's going to be this statement right here. The large truck can pour a foundation 25 minutes faster than the small truck. So however long it takes the large truck, so the time for the large truck is 25 minutes faster. So if I add 25 minutes to this time, that'll be the time it took the small truck. Does that make sense? If I have 40 minutes for the large truck, does it make sense that the small truck would be 65 minutes? Does it make sense that that number should be bigger? Yeah, so we're pretty sure we've got that right. So TL plus 25 equals TS. So what I'm going to do is I'm going to take this TS and replace it with this TL right here. So we're just going to do a substitution. Okay. So we're going to substitute and then solve this for TL. So we have 1 over 40. I'm going to drop the units now because they're just going to get in our way. Plus 1 over TL plus 1 over L plus 25. Oops, 25. There we go. So I just took out the TS and I put TL plus 25 in there instead. Now we need a common denominator just like before. This is why it's a little bit harder because the common denominators can be a little wonky. This is TL and this is TL plus 25. Because of this plus sign, you can't just put a plus 25 plus 25. That's not really how math works. We have to multiply this by something. So what we're going to multiply this by is TL plus 25. Okay. Here, we already have a TL plus 25, but we're missing the TL without the plus 25. So on this one, we're going to multiply by just TL. Okay. So over here, this is still 1 over 40. This 1 times anything is the anything. So this is going to be TL plus 25 over, here we need to distribute. So TL times TL is TL squared, and TL times 25 is 25 TL. Plus, right there from between the fractions, 1 times TL is TL. And then same thing here. This should be a TL. I don't know why I put a thing there. TL distributes, so we have another TL squared plus 25 TL. You'll notice that your denominators match here. That's the whole point of what we just did. So the fact that they match is good. Now we're going to combine our fractions. When we add fractions with common denominators, the denominator stays the same. So this is TL squared plus 25 TL. And on the top, we just combine our like terms. So TL plus TL is 2TL. And then bring over our plus 25 because it doesn't have any other numbers without variables to add to. So this is our combined fraction from here. And now this thing looks a lot more like a rational function we've been dealing with, right? And that equals the 1 over 40. Now we have to solve this thing. So to solve this rational function, we're going to cross multiply again. That's anytime you have a fraction equals a fraction. To get rid of the fraction so you can solve this, you do cross multiplying. If that equal sign isn't there though, you're not allowed to do that with fractions. Like you can't cross multiply these because this is a plus, not an equals. All right, so 40 times this top thing. We need to distribute the 40 to the whole thing. So that's going to be 2 times 40 is 80 TL. 40 times 25 is 1,000 equals 1 times anything is the anything. So we have TL squared plus 25 TL. Now this is a quadratic, and we know that because our largest exponent is a 2. That makes it a quadratic, right? So to solve quadratics, what we want to do is move everything to one side, and I try and move it to the side with the t squared, and then we either factor it or beat it to death with the quadratic formula. So let's start by moving this and this over here. So to move this over, we're going to do minus 80 TL on both sides and minus 1,000 on both sides. And I usually put the 1,000 over here because there's not a number by itself. That way I don't accidentally combine things that aren't like terms. So these obviously cancel and it equals 0. That TL squared doesn't have any other squareds to combine with, so we just bring it down. 25 minus 80 is negative 55 TL. And then the 1,000 doesn't have a like term, so it just comes down as well, minus 1,000. Now this thing is probably not factorable. You could sit and try and guess 2 terms that multiply to negative 1,000 and add up to negative 55. But because I know the answer to the question because I've already done it, we're not going to mess around with that. It's too scary. I don't want to. What if I accidentally try really hard and it doesn't factor? Then I just wasted all that time. So let's just use the quadratic formula straight away. So A, there's no number here, so it's the invisible 1. B is negative 55, and C is negative 1,000. Now I plug these into the quadratic formula on a computer, and I just got some numbers. So let me tell you what the numbers are. TL equals, hold on, let me find it. Where did I write it down? There it is. Negative 14.407 hours. And because you get a plus and a minus, you get 2 answers. The other answer is 69.407 hours. Now we need to talk about real life for a moment. If I'm pouring concrete, can I, oh, I'm sorry, these aren't hours. I misspoke. These are minutes. Minutes. If I'm pouring concrete, I throw the lever and the concrete starts coming out. Does it make sense that I finish pouring my concrete almost 70 minutes later? It takes about an hour to pour the whole thing. Or does it make sense that 14 and a half minutes before I started pouring the concrete, it's already done? That doesn't make any sense. How can you finish before you started? This is an extraneous route, not because we did math wrong, but because you're not allowed to go backwards in time in real life, as far as we know. If you know how to, please tell me. So we throw away the negative one because you can't have negative times in real life. So the time it took us for the large truck to pour all the concrete for one house is 69, and we'll just round, 0.41, whoops, sorry, not, get rid of that decimal, aw shucks, 0.41 minutes. So it takes about an hour and 10 minutes. Now we still have to go figure out the time for the small truck. But luckily, this one's pretty easy. The small truck time is the large truck time plus 25, right? And we know that just from this sentence. The large truck can pour a foundation 25 minutes faster than the small truck. So we already know how long it takes the large truck. We're just going to add 25. So the small truck can pour it in 94.41 minutes. And those are our two answers. All right. That was long. That was a 45-minute video. God bless America. I'm sure you have some questions. 45 minutes for 3 questions, Barton? Don't worry. If you're not listening to me tell jokes and explain, they go a little faster. But if you need any clarification, go ask me. I'll be happy to help. If you're not my real student, I'd still be happy to help, but good luck trying to figure out how to contact me. Have a great day, you guys.